Okay, is everybody done with the quiz, or just the people that came in? Okay. Well, Professor Nobi had an emergency, so you'll have to bear with the Greek accent for another class. Let's just give it a minute. Okay. So in the last class, we talked about condition generation, right? We talked about the encoder-decoder model and how, given an input sequence, we can generate an output sequence. Okay, just checking that everything's okay with the quiz, right? Okay. So in what we saw in this encoder-decoder model, let's say we had a Japanese sequence and we want to generate the English translation, and we said that we have an encoder that creates a representation for the source sentence that we fit into the decoder, right? And the decoder is basically a language model that receives the context through this arrow here. In the last class, we said that just for them that will represent the input, the whole source sentence as the last vector from the encoder, right? However, to quote Ray Mooney, you cannot cram the meaning of a whole sentence to just a single vector, right? Maybe it might be true for really short sentences, but language is very complex. You can have sentences of up to 100 or 80 words long. So just a single vector, unless it's really, 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 really big, to the point that becomes computationally infeasible to deal with it, it's not doable. Or it's doable, it's just, it's not the best that you can do. So what if instead of just one vector, we had multiple vectors based on the length of the sentence? So in this example, in the sentence, this is an example, instead of taking just one vector, what if we took a vector per word, or per character, or per word piece, or per, I don't know, byte, if you wanted to do that? Okay, so what if we had multiple vectors that represent our source sentence that we will then provide to the decoder? And the question is, how do we provide them? The answer is with attention, okay? So the basic idea is as follows. Again, the encoder, what it does is produce representations for each word, or again, each word piece, or subword, or character, okay? And then, during decoding, you want, instead of just having, you want to combine all of them into one vector according to some model. And what we use in this attention idea is that we will create a linear combination of all those vectors, and the weights that we will use are these attention weights. And we'll see how we can compute them. And then this linear combination basically will provide you with the context that you might need in order to generate the next word. So here's the general idea again. We have our source in Japanese, and we have the representation for each word. And we're at the decoding step where we have generated I hate. And now we have two things. We have the query vector, which is the current state of the decoder. And we have a bunch of key vectors that are all the states that we got from the encoder, right, of the words in the source. Now, again, the query and the key vectors. And now what we'll do is, for every pair of a query and a key, we'll somehow calculate a weight. And that will tell us how important the query thinks that each of the keys will be for generating the next word. So we do that somehow, and we get these numbers for each of those source vectors. And then we just normalize them so that they add to 1. And they seem like they are basically a probability distribution over all the input words. And now we have these weights. over all the words that we want to use in order to generate a single vector that will be our context. So what we do is we combine them by taking the weighted sum, right? We had 0.76 for the first word, 0.08 for the second word, and so forth. So we get the weighted sum of all these. And now we have this vector, which is the context that we will use for the next step, okay? And because it was dependent on the current decoder state, when we, because the way that we calculated those weights was dependent on the query vector, okay? Then at every time step, we would want, or we would expect to see that we will take different weights as we unfold over the sentence, over the generating sentence. And this context vector can be used at any part of the model you like. You can feed it into the decoder as another input. You can, if you wanted, take it into account when you compute the state of the decoder in a different way. You could provide it to the model right before the softmax and after the LSTM in order to bias somehow the output. The key concept here is that for every time step, we will have a different context vector exactly because we have different weights as we generate. So here's an example from with translation from Japanese to English. I don't speak Japanese, but I trust that it's a decent example. And what you can see is, and I'm pretty sure that restaurant, lighter means higher weights. Restaurant more or less attends over what it should. There are some things that are not attended to, like there's nothing constraining, telling our attention exactly what to do. So, and we'll talk about it later. So this is just an example of what the final weight, the weights as we move down or as we generate our target sentence, how they can change as the decoder state changes. So before we mentioned that we will somehow get these attention weights. Let's see how we can do that. Again, Q in all those cases will be the query, the state of the decoder, and K will be the key for every source word representation. So the first proposed model was by Bahdanau and others in 2015, and it used basically a multi-layered perceptron. For every key and the query, you would weigh them and combine them this way. And this has a lot of parameters. You have this W1 and this W2 that you need to learn. However, this makes it quite flexible. And if you have a lot of data in order to train your model on, this is a pretty good option. Another thing that you can do is use a bilinear score function, which combines the decoder state and the key like that. So basically, you take the dot product between the two, and in between you might have a vector that will allow for different dimensionality. Another thing that you can do is, if you do have the same dimensions between the query and the key, you can just take the dot product, right? And that needs no new parameters. Ideally, the keys or the query will learn to also be useful for that task, for the task of computing the attention weight. But it has the drawback, this thing. So this option does not require new parameters, but it does require the two sizes to be the same. And then recently, Vaswani and Google Brain noticed that this dot product has this a very simple problem, that as you increase the size of these Q and K, then the scale of the dot product increases too. So in order to keep this constrained, they proposed the scaled dot product, where it's basically the exact same thing, except the final output is normalized by the size of the vector. Okay? Yeah? Okay. So there's code for you guys to try it out later. So let's talk a bit about, we have all these different attention functions, and it might be up to you which one you would use, or there's some general guidelines, like how much data do you have, how many parameters you might want to have. But what can we attend over? So as before, in an encoder-decoder example, like in the previous explanation, we'll just attend over the source sentence, right? Which will provide us the context at each decoder step. Or we could have something even more direct. Cohn et al. Proposed to use a copying mechanism. So let's say we have the attention, and at a decoder, at some step, we have the weights over the source. Now we could use that as if it was something like alignment, although we'll talk about it later. And wherever you're attending over with a higher weight, what if you just use that to copy that word, right? And in that particular model, they had the final softmax, the final output be the interpolation between the decoders, the generation model, and the copying mechanism. So why would you want to do that? Any ideas? Why would you want to copy something from the source when you're, for example, translating?
Unknown words.
So that's one thing. Or like very rare words that you might not have in your fixed word vocabulary. Or even you want to make sure that you use the correct word, right? Especially with named entities, which are, again, rare words. We talked before about how the decoder is a language model. It's a conditioned language model, but it's still a language model that will prefer more common words rather than rare words. So by having this copy mechanism, when you're talking about, I don't know, countries, you might not always talk about USA and Britain, but you might, because their embeddings would be very similar. There's some work on that. So you might want to essentially learn to copy from the source using this attention mechanism. Another thing that you might want to do is, if you have a discrete lexicon, that's work again by Newlab, and you want to incorporate that so that if you're attending over one word with a very high weight, and you have a lexicon that gives you candidate translation, you could potentially use that. Another thing that you can attend over is previously generated. Yes, sorry.
So how do you decide when you copy a word, when you not? Is it with just when your model generates UNK, so you choose to copy, or just say that
So was the question about how the copy mechanism works?
How do you decide when to copy a word?
Oh, let me see. I don't remember if it's here, but remember how we said that the final output would be a linear combination between the output probability from the decoder and the output from the copying mechanism. So you could eventually, actually, sorry, let me backtrack. You could learn if you want to copy or not. So that you could have another parameter in your model that is, for example, a 0, like outputs a 0 and 1. And if it's 1, you will use the copying mechanism. If it's 0, you would use the actual decoder. Or you could, again, combine them by some weight that you also learn. Okay? So, yeah, so other than just the source sentence, we could also attend over previously generated things. So let's say we have generated like Fed Chair Janet Yellen, blah, 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 raise the rates, dot. And Mrs. Now this is for cases where you want to have longer generations and coherence across. And instead of just looking at the source, if you have a source, right, in the encoder, you could have an attention over all the previous words that you have generated. And in that case, you might want to see that your pointer component here will attend over the correct word, the name, Yellen. And you could have the final softmax be, again, the combination of what your RNN generator is producing and the pointer over the previous words. Okay, that's just to to give you the idea that you don't only have to attend over a source sentence. It's there's people who have used attention over the previously generated words for language modeling, so without having anything to condition on.
Excuse me.
Yeah.
Does this mean that you have to save a dictionary for previous generated words and about
Not really. Why? If you have already generated them, right? If you have a sequence of...
Yeah, let's say if the main Jenny you haven't mentioned appeared in the previous sentence,
Mm-hmm.
and then to look up the pointer probability for Jen, then you have to say this number.
Well, if you think about the way that you construct a computation graph when you're building a neural net, right? In the case of language modeling, your computation graph, this whole computation graph from the past already exists, right? And you have done the forward pass through it when you're about to generate that word over there. So all these things exist, and you can just have your attention mechanism attend over, say, the decoder states or something like that. Or even if you have the correct words that you wanted to have generated, you can attend over their embeddings or something like that. So I don't think that you need to have something like a dictionary or to just keep it, because you already have it. That's my point. Okay. On top of that, you could, and we'll talk about the transformer model later, you can do both. You can be attending both over some input as well as any previous output. Okay, we'll see about that in a little bit. Now, there's nothing constraining us to using attention with text. We could attend over images, like in this work where after a bunch of convolutions that extract features, in order to generate a text caption, the decoder had received context through attention, and in fact, I think it was attention over the three different color channels of the image. Or you could have your input be speech, in which case you might be attending over feature frames, or in fact, what people usually use in speech is you have an encoder that restricts the size of the input, because speech the input in speech is, the features are usually very fine grained, as in a feature every 10 milliseconds, and then you constrain the length, and then you use that representation to attend over. And you can see again, this is an example where indeed the attention follows the generation. And one more thing that you can do is use attention in a type of hierarchy and attend over hierarchical structures. So in this work, the task was document classification, right? So a document is comprised of many sentences. So what they did is, in the bottom, for every sentence, they read in the words, they had the embeddings, they read the words through an RNN, and then they attended over the representations of each sentence and got a context through the attention. And that way we had one representation for every sentence. And now, on top, having that representation over all the sentences, they put them through another RNN, and then use attention over that in order to produce the final classification. Okay? All right. Or, going further, there's nothing stopping you from having more than one source. So in this work by Zoff and others from USC, what if you had two sentences that you want to attend over in order to translate? Let's say you have German and French, and you want to create the English translation. This is not necessarily useful, because why would you ever have this type of like trilingual text? But the case is that lots of work on machine translation was done on corpora that were created by the European Parliament, which by default translates everything into 17 or 20-something languages. So you do have this type of n-parallel corpora, and in this work they show that you can have two sources on two languages with two different attention mechanisms that provide context to the decoder, and you can do a better job, basically, at translating if you have multiple sources. An interesting study that compares the different strategies for combining multiple sources can be found in this paper. We won't talk more about it. And again, there's nothing stopping you from having multiple sources where more of them, one of them or all of them or whatever are not text. So there's this work where they had an image, they extracted features, they also had the caption in English, and now they had an attention over the image features and the English caption in order to create the German caption. Finally, this is quite similar to attending over things that you already have. There's self-attention or intra-attention. Now, in this case, remember, all we need for attention is a query and a bunch of keys. Okay? And what if we have a sentence? The sentence, this is an example. And for every word, we had the word itself be the query, and the keys are all the other words, all the words in the sentence, including ourselves, and hence the name self-attention. So what we have here is, let's say you have embeddings for all the words, okay? And for the word this, the embedding for this becomes the query. We calculate the weights over all the keys. We get the weights, we get their linear combination, and we produce a new representation for this, for the word this, okay, that includes information from its context. So we can do that for all the words. And now instead of the typical embeddings that you've talked about, now we have context-sensitive encodings for every word. This is, again, we'll talk about it later, but that's the main idea behind the famous transformer model. And yeah.
I was wondering, will the time complexity not increase because now you have a quadratic combination to get to each word?
Right, yeah, so now the complexity is quadratic over the length of the sentence. Yes. So before we go into the latest things, let's talk about some not tricks, but like some improvements that you can do in order to make attention make more sense or generally work better. So the first thing is coverage. Even in the example that we saw before, the Japanese to English one, right? There's no guarantee that the decoder will take all of the source into account. In fact, that was one of the major problems in the very beginning. Who here is familiar with phrase-based machine translation? Okay, cool. Okay, anyway, so before NeuralMT was all the hype and everything, the best thing that people had developed was phrase-based machine translation. And there was a toolkit called Moses that had a decoder, just like we have an encoder-decoder, not a neural one. But what it did is we had candidate phrases for every source phrase. So the decoder, in order to create a translation, the Moses decoder, in order to create a translation, run through all of the source sentence, combining all the candidate phrases, and then there were some scoring functions like reordering, etc., that you don't need to care about. But the point was, in order to create the translation, it covered all of the source sentence and created a translation for every source word. Now, in the neural realm, neural models tend to drop words, to drop content, or repeat content. When you start, if you haven't already, training a language model or a translation model, in the very beginning, hopefully, and only in the very beginning of the training, you'll have outputs like this. Okay, so what's the solution here and incorporated with the attention mechanism? We want to model exactly how many times the source words have been covered in order to make our model, attend over all of the source words and basically, ideally, attend over the source words once. So there's many ways that you can do that. Trevor, Cohn, and others proposed adding a penalty at the loss function where, remember the attention weights that we showed before? So, and we said how we normalize them to sum to 1 per row, right? Now, if we add the penalty and we ask the model to basically also sum to 1 per column, that essentially will mean that every source word will have been attended over with a total weight of 1, okay? So that's one way. The other way, by me and others, is having an explicit embedding that indicates coverage that you take into account when you compute the attention weights. And at the end, you penalize, you start with an embedding weight of 1 for all the source words, and you want that when you're done generating the sentence, that embedding will be down to 0. Basically, you think about it, you subtract, one of the methods that they try is when they generate an attention weight, attention weights for each step, they deduct them from the budget that you have for attending over all of the source words. So the idea is as you generate more and more attention weights when you generate the target words, you deduct and you reduce your budget, and eventually when you're done generating, you want to have a budget of 0, which means that you have looked over all of the source words. You can find more details in the paper. Another idea that was also that also existed in the phrase-based world is incorporating Markov properties on the alignments. So the idea here, the intuition is that for alignments at least, it was that the attention or the alignment from the previous word could be useful or could correlate somehow with the alignment of the current word that we want to generate. So what Cohn and others did, so here's an example which, again, is not the attention weights are not exactly aligned with what you think the correct translation pairs would be, but you can see that even though the attention is jumping back and forth, again, the idea is that in the different steps, as you generate the output, the alignment or the attention, it might make sense that it could be dependent on the previous one. So I don't know Japanese, okay? I don't know if this is correct. But for you, we mostly attended over those 2 characters over there in the middle of the Japanese sentence. So maybe it's reasonable that also for the next word, we want to attend over them. Maybe. So you can incorporate those type of biases or actually model these Markov properties, and Cohn and others did a good job at that in that paper. By basically providing the previous attention vector as an additional input in the function that computes the next attention weights. Finally, in the same paper, here's another intuition. When we train an English to French system, we get a bunch of weights for a sentence, okay, on top. Now, what if we had a French to English system, and we get those weights, and now naturally we would want them to match, okay? If when we generated, we don't have examples here. Oh, the example is Estonian. Anyway, when we're generating maison in French, and we see that we're attending over house in English, then in the opposite case, when we're generating house in English, we would ideally want the models to learn to attend over maison in French. Okay, so they formulate this as a bonus, and a bonus during training. So here they train both systems at the same time, both English-French and French-English. And there's an additional, here it's not a penalty in the loss function, it's a bonus. That is the trace of the multiplication of the 2 attention matrices, right? So maximizing the trace means that you maximize the weight that's on the diagonal, which means that they agree more, that the 2 attention matrices agree more. All right. Finally, what if we have some gold standard alignments? could we use them? Again, from the phrase-based world, one of the first things that you did when you had a parallel corpus is you would run an aligner, like typically a combination of the IBM models, and you would, which you would then use to extract phrase pairs. In this case, if we have gold standard alignments annotated by humans, or if you have a strong alignment model that could give us, again, gold or silver standard alignments between the source and the target sentence, then maybe we could use them and basically force the attention mechanism to be like them. And you can train the model to match those strong alignments. So you can have a loss function, for example, that for every target word that you generated, you knew what it should have attended over on the source, and you can encourage that in the loss function. However, and we talked a bit about how we are trying to make, with all these models, we're trying to make attention look or be more like the old school alignments that we had in the phrase-based models. However, as Philip Cohn and Rebecca Knowles noted in a really good paper that I encourage you to read on the shortcomings of neural machine translation, one of them is that attention is not alignment. Quite often when you train, you'll see that compared to what you would expect, attention is always off by one, right? So you can see here that the highest weights in this example are always a step next to what you have expected them to be. And the other thing is that it's like alignments were binary. They were 0 and 1, either between 1-to-1 words, or you could have them be like between 2 and 2 or 1 and 2, etc. But yeah, attention could be more blurred, right? So here down here at the end, when you're generating the last words, you might want to be attending over a whole phrase, or the equivalent of a phrase, or a bunch of source words. Okay, so keep in mind that even though it was shown that trying to make the attention look like the old school alignments helped, attention is still not exactly alignment, and I don't personally think that it should be. Yes?
So if the attention is not alignment, then how does this help with translation? Because this says that you are trying to, so the model will focus on the wrong word to translate. So how does attention help in this case?
That's not necessarily true. That the fact that it would, the sentence that it focuses on the wrong word is not necessarily true. Because if you think about it, you have the words, right? And you have all their position and everything, and then you put them through an LSTM. And is there any guarantee, although there are some studies that show that, but is there any guarantee that the information stays in place? You have all these recurrent connections, and quite often you have many layers. So what is there to tell you that the first vector that you got encodes similar information to the first word on the very bottom? Okay, so that raises an interesting question. So there's another thing that using multiple vectors and attention does, and some people claim is, remember before we only used one vector that was the last one that the encoder LSTM had produced, right? And if you think about the way that information flows between the encoder and the decoder, and the way that we train with backpropagation, this last vector, encoding all of the meaning of the source word, is essentially a bottleneck through which the information has to flow forward and the gradients have to flow backwards, right? Instead, when we have attention, we have several paths, and different paths for every time step, connecting the decoder to the encoder when we do backpropagation. So, like the gradients flow more easily between the two, and it's easier to train. Okay. Right, and there's a bunch of other specialized attention varieties that we can go over. One is to use hard attention. So before, our attention weight was a probability distribution over the source words. And what if we, yes, sorry.
Sorry. So why is it often off by 1, not by 2 or by 3?
I don't know. I don't know. It doesn't always happen too. It's, yeah. Sorry. Yeah.
Could it be because you're feeding in the previous attention vector, the attention vector, the previous step as an input?
Well, the off by one thing doesn't only happen when you're using this variant where you are using the previous attention vector. Like in the standard original Bahdanau model, if you run that didn't have all these extra things that we talked about, that was also often off by one. So, yeah. Yeah. Okay, so back to hard attention. So here, instead of having this soft mechanism, we make a 0 and 1 decision about where to attend. So basically, we'll talk about it much later in class, and you can do that with reinforcement learning. But the main idea is that you would convert this soft this probability distribution to a 0 and 1, or you can encourage it to be more binary, and it's harder to train. However, this could be very useful in providing explanations, right? So let's say we have a task that is reading a text and coming up with the rating that corresponds to that particular text, right? Like sentiment analysis or providing movie ratings. Well, that's about restaurant or a beer place, right? So if you force your attention to be a 0 and 1 function, have it out to be a binary function, then you would know that the part of the source that was responsible for that output of 5 stars is that particular segment which you attended over, right? So that could be something very useful. Another thing that you might do is to encourage the attention to follow the diagonal, to be monotonic. And why would you do that? There's many cases where that's the expected relationship between the input and the output, right? So one is speech recognition, right? When you are transcribing speech, you don't want to mess the order at which things were uttered, right? Like ideally you would transcribe every sound that is made in a chronological order, in a left to right or right to left fashion. Or if you're doing incremental translation, then that's similar more or less to interpretation, right? Where you're producing translations of chunks and you want your attention in that case to be monotonic over those chunks. Or again, morphological inflection, maybe, or summarization, again, maybe, right? If you're summarizing a book, in a hypothetical example, right? Quite possibly you would want the first part of your summary to be about chapter 1, and then the second one to be about chapter 2, and the third one to be about chapter 3. So again, you'd have a monotonic attention over the chapters, for example. So there's this work by you and others. There's this example from morphological inflection, where the task here is given a verb, in this example in German, and you want to train a model that would produce the infinitive, I think, version of that verb. So zocken would become gesorgt. And in that case, there was this model where they, what they did is they hard decisions about whether to read more of the input and create output, or to maybe skip the input or something like that. In the same way that an FST might, read in the input sequence and decide to output things or read in epsilons. Finally, there's this idea of convolutional attention, which basically uses convolution to have the queries be specific words that you might want, And the idea is that you might want, if you're doing, say, entity extraction or something like that, or retrieval, right? And you know that names come after the word Mr. or Mrs. or something, and you want to extract them, then you can have a convolution type of attention that would only return you the output after the specific query, which would be Mr. That's just an example. You can read more in that paper. Finally, what stops us from, remember in the decoder we said that at every step we generated one attention, one vector of attention weights over the source. What if we generated more? So what if we had several heads producing different distributions over the source word, which might capture a different aspect of the source? So one example, coming back to our copying mechanism, is let's say we have two heads. One that learns to provide context to the decoder, and one that learns one that learns to attend over the word that we might want to copy, right? Or we might have several independently learned heads that we don't guide them whatsoever through the loss function. We just have several attention heads, and we tell them to learn whatever they want. And in this work, in the transformer model that we talked about earlier, they did do that. So they, instead of just generating one distribution of weights over the source, at every step they have 8 different heads, and they showed that during that improved results a lot. And basically, they showed that some heads could potentially learn to capture syntactic features. Other would learn to capture something more related, for example, to semantics or something like that. So that's always an idea. Another one is that you can even have like different heads for every hidden node, but that's also a recent work. Yes?
How do you make sure that different head or different attention vectors actually learn different things?
You don't. So actually there's some recent work that does that. So in the original transformer paper, they didn't. They just, instead of receiving a single context from a single attention head, they receive 8 slightly different contexts from the different 8 attention heads. You could, for example, in this recent work, you could encourage the heads to learn something different by having a loss function that penalizes heads that are the similarity across the outputs of heads.
It almost sounds like MMR.
Maybe?
The maximum marginal relevance.
Maybe, I don't know. But if you think about it, each head outputs a vector, right? So in the same way that we have vector similarity metrics. So if you turn them into a penalty in your loss function, during training, you ideally would learn weights that are diverse. Another thing that was recently proposed by Emma Strubel and it was part of the idea that got a Best Paper Award is what they did is they made one of the attention heads to be exactly similar to what a dependency parse tree would look like, more or less. And that was like linguistically motivated self-attention. All right, so let's talk about this paper, Attention is All You Need, that came out about 1.5 years ago, and they proposed a transformer model that has become the de facto thing for people to use, and the idea in general of self-attention has become recently. How many people have heard of BERT? Okay, so again, the idea of self-attention and of the transformer has basically revolutionized the NLP field. So the transformer is again a sequence-to-sequence model, okay, that does not have any recurrence. So we do not have any RNNs or LSTMs or anything. So, however, the idea of the encoder and the decoder is still there. We still encode our input using now self-attention. This means, remember how we, in the example that we saw before, this means that at every layer, each of the words gets the chance to be the query. We comparing with all the keys on the same sentence, we get weights over them, and then we compute the next layer representation for our word by having it be the weighted combination of itself and the context, basically, right? And we do that over several layers for all the words, so that's quite expensive. And there's other tricks that we're going to talk about, but essentially using self-attention and not using recurrence, we get a final representation after, say, 8 layers of self-attention. We get a more informed representation of the source sentence rather than just simple word embeddings. Is that slightly clear? Is it clear? So no recurrence, no LSTMs, or no RNNs. Then the decoder combines two things. It combines the standard, like the attention over the source representation that we computed, with multiple heads, etc. And attention over the previous word that the decoder has generated already. We'll see an example of that. And basically the takeaway is that this model blew everyone's mind because it was so strong on the WMT data sets, especially when you have a lot of data to train on. Currently, you cannot do better than a transformer. And because it's after training, when you're done training, all this thing has, since it doesn't have any recurrence, it has only attentions and some multi-layer perceptrons on top of them. It consists only of matrix multiplications, so inference is very fast. Okay. So in this paper they do a bunch of tricks. The first one is, it's not a trick, but they're using self-attention, and each layer of the encoder as well as the decoder basically combines context from each sentence to compute the representation for every word. They also use multi-headed attention, and they started with 8 attention heads that were learned independently, meaning that there's nothing tying them together, or they have different parameters for each one. Although there's some recent work that shows that you might not need all of them. And each of those attention heads used the dot product attention that we talked about, which was just the dot product between the query and the key, but normalized it in order to deal with the bias of the dimensionality. Finally, there was another issue, right? Convolutions or recurrent networks, because they go from left to right or from right to left or both, they still have a notion of positioning, right? When you have the RNN, it would ideally remember, it would have a notion of which word came when. In this setting where we only have self-attentions for every word in the source sentence, right? There's nothing that will encode position. And we found that, it's not easy to translate a bag of words because there's information in the ordering of the words, right? So what they did here is they create a positional embedding, which basically it's a number that you can get. They use a cosine, and every position gets a different number, which is basically a number that encodes the position of each word in the source sentence, and they provide that as additional input along with the word embedding, and that's very useful because it allows the transformer using only self-attention to distinguish between whether the word that we're dealing with is on the beginning of the sentence, or it's in the middle of the sentence, or it's on the 8th position of the source. Furthermore, they use layer normalization that would basically, after every layer, you make sure that the norm of the weights are constrained and they remain in the original range. One implementation note, in the original paper, they describe the computation flow. Let me backtrack. They also use residual connections. Do you guys know what these are? Okay, so they use residual connections across layers. So what they originally had in the attention result unit paper is have the residual add and then do the layer normalization, which basically breaks the residual path across layers. Now, all the popular implementations of the transformers that are out there, like the tensor to tensor, the FAIR-SEQ implementation, the OpenNNT implementation, they switch that to doing the layer normalization node before they add the residual connection. And that significantly improves the way that the model behaves. The only problem is that not all papers note that distinction, but it significantly improves the way that you can train it. Another thing that they have in this paper is this specialized training schedule. So instead of having, starting with a default learning rate for Adam or for SGD and just let it do its thing, what they had was they had a burning period where the learning rate increased linearly, and after like 10,000 or 20,000 or something steps, then they decreased it. So one of the reasons that they had to do that, it was later, there were some discussions, you can find some blog posts, and they explained that if you make that swap in the computation, and you do the layered norm before adding the residuals, then you might not need that weird learning scheme. And you can just use Adam or SGD. One more thing that they did, like this paper was full of tricks, okay? Or like common knowledge that had accumulated and all of it combined into something beautiful that works great. It was label smoothing. Have you guys seen this? Have you seen this before? Or so label smoothing is basically when you train, instead of having your output distribution wanting to be in one hot and telling your model that I want you to predict with 100% probability that one word, you include some uncertainty and you make the probability of the correct words slightly lower, like 0.9, and then you distribute the rest probability of the probability mass to all the other words, essentially making the model a little more uncertain during training, but that helps generalization and the performance in the end. Finally, in order to, because the original paper had 8 layers on the encoder, 8 layers on the decoder, 8 attention heads, it had a lot of parameters. So they had to find a way to efficiently train the model. And what they did is masking during the training process. So basically the main idea is, since the encoder and the decoder, they're all comprised of attention or self-attentions and basically simple matrix multiplications. What if I'll have them all together, let me show you here, and we want to parallelize everything, so can we do big matrix multiplies instead of doing everything all at once or each layer at once. So if you mask the decoder part that is the output when you compute the loss, or when you tell the decoder what it has seen already. So when we have seen just the source, right, the black parts are the things that the decoder can see because it can attend over them because it's the source, okay? Now, in the decoder side, after in the next step, when we have generated the first word, now we can attend over it. So they kept doing that, and the mask keeps reducing, keeps at every step. We removed the mask over the words that we have already generated. So by doing that, basically, this whole computation can be propagated all at once through, right? By not having these white parts available when you do each step. I'm sorry, I didn't explain very very well, but you can find. Oh, that's it. I don't have anything else. Yeah, there are. One second. There are several blog posts online that you can go through that explain why maybe some of these tricks are important or not, and how all of them combined can make the transformer model work really, really well. And yeah, I don't have anything else. I'm sorry if I ran through things, but we can have a discussion now. Yeah.
Ask for training. Asking for training. Are they using this together with the self-attention method?
So this is the mask over what the decoder can see at every time step, right? So when we're generating the word this, we want to only attend over these two, right? But the thing is, the way that this is implemented, if you think of this as a big matrix that can be fed directly into the decoder and have the create the computation graph, etc., then when you propagate back, you will not use in the forward or the backward path these parts, right? So this is a binary mask. These are zeros, these are ones. So by having that mask, you can in the actual implementation, you can, instead of doing decoding at multiple steps during training, you can do that all at once. Yeah.
My question or my confusion is that it's sort of like you're doing self-attention, but shifted as
You're doing self-attention where?
later on, we are including the range of the mask into the output sentence, like from I to I did this, I did this. And you're basically doing an attention not only on the input, but also on the part.
Yes, that's correct. So the transformer model.
Yeah, what is even extra self-attention?
Yeah. So the encoder only has self-attention and creates a representation for everything. The decoder has both. The decoder has attention over the source and the self-attention over the previously generated word. So essentially, that's exactly what this mask encodes. There was a, yeah.
So with the regular LSTM model, you feed in the words, input words, word by
With
word.
the what model?
With a simple sequence to sequence model like LSTM, you feed in the inputs word by word. But I'm not sure how is the input and output fed to the transformer model, and how is that trained?
Oh, okay. Yes, you do fit it word by word, but when you actually implement it, right? In fact, the thing is you have all the words already. So the difference is that the computation graph goes from left to right. If you think about it, when you have an LSTM, right? When you have a transformer, so if these are the words, right? And these are the states of the LSTM. As it unfolds over time, the computation graph has this type of connections. In the transformer, the connections, in order to get the next representations, are basically like this. For all of them. So for every word, you have connections coming in from all the source words, including itself. And of course, okay, this is very simplistic, right? There's the attention in between, there's an MLP, and all those. But the point is that now you don't have this left to right flow of information.
So what are each of those vertical lines? Are those for particular words?
Oh, this one?
Yes.
Oh, let's say these are the embedding. These are the word embeddings in the very beginning. And then here you have another vector of some size that is the contextualized representation that we will talk about in the next class. The contextualized representation that has used the self-attention in order to produce another representation for this position. So yeah, so you have, basically you create more and more informed vectors for every position in the source word. Okay. Yeah?
I didn't quite understand what makes the transformer network better than the LSTM network. I mean, I understand the results of it, but is there any theoretical analysis?
Well, I don't know if it's like concretely theoretical, but the recurrent connections, the idea that you can encode really long-range context in a left to right or a right to left manner is a bit ambiguous, right? So yes, theoretically an LSTM would be able to do that, but does it? I don't really know. However, in this case, at least on the source side, right, every source word looks over all of the other source words. Even if you have 80 a sentence of length 80, then for every one of those words, you would do 80 comparisons, and potentially that would inform your next representation. So it's probably better at capturing long-term dependencies, probably. So that's one thing. The other thing that might be important, yeah, I don't know. Yeah, so that's possibly one of the things that make it better. And this is further reinforced. We'll talk about in the next class about contextual sentence representations. Basically, they employ very similar ideas, and they also seem to work. So there must be something better happening there.
And also you mentioned residual connections, so where exactly do they come into play and how do they help you?
Oh, so between every layer in the transformer model, basically you add the residual connection between, I think, if I remember correctly, basically the residual connections are like that. Right, so there's a series of computations that happen in every transformer layer. Let me see, I have it here, right? So on the left, that's the one layer of the encoder. So we have first the component on the bottom that computes the weights of the self-attention, and the other norm computes the context, the linear combination that we talked about. And then you have a feed-forward NLP, basically. And if I remember correctly, there was the residual connection might be that thing on top, which in the actual implementations, they changed it to be to come from all the way down. So the claim is that by having it the way that it was now, you have the layer norm disrupt the paths between the residual connections. So there's a residual connection from layer 0 to layer 1, and another one from layer 1 to layer 2, and in between you added a layer norm that disrupted that path. And one of the points of having residual connections is allowing the gradients to flow not freely, but better between the layers. So if you disrupted that path, you made it much harder to train. Yeah. Yeah.
So how do we control the logic and attention and learn different parts?
How you can control it?
Yeah.
There's this recent work that I don't remember by who it is, but we might be able to find it and post it on Piazza. So that's the thing that one idea, okay, would be to to encourage diversity across the different heads, right? So as I said before, if you have the vector that each head produced, you might penalize similarity across them. Another thing is if you have specific things that you want the heads to learn, like you want one head to learn syntactic dependencies, right? You want the will have to have a connection from have to will, or to have a high weight between the two words that for some reason you think that they should be connected. Or if you have a German sentence where I'm translating now in English, but if it's something like I must something do, right? Where the order is different, but you want the two to be connected, and you know in advance that you might want such a connection because you say, let's say you have a syntactic tree or a dependency tree over the source sentence. You can encourage, through training again, have a loss function over, say, one of the heads to make the weights of the self-attention match edges of that tree. Maybe. Well, you wouldn't necessarily, it's not exactly multitask learning, right? Because you're not trying to do a new task, an additional task, but you're just encouraging your head to capture specific information that you might have.
To that, we should be parameterizing each head.
Sorry?
To achieve that, we should be parameterizing each head. Because without any parameters.
Okay, the original claim, what do you mean by parameterizing each head?
Like, you just can't do dot product attention for all the heads. That would give us the same. For each head, you might have a parameter or a matrix which calculates the attention.
Well, in the dot product that the function, the attention function that we use, we don't really have any additional parameters for the actual calculation of the weights.
Then how do you have different attentions generated by different heads? There should be something different between each head, right? Some kind of parameter or something should be.
Yeah, that's it. Well, you're right. But the thing is, I need to think about it. The truth is that well, let me come back to you on that, right? Because I'm sure that they use the scaled dot, the normalized dot attention, which does not have any additional parameters per se, but there are other stuff that are happening. And basically, in the original paper, they don't do anything about guaranteeing that the heads learn different things or anything. It's just that it might just be that. Look, I'm not sure. But they do show that some heads learn different things. Yeah.
I have two following questions on the architecture itself.
Uh-huh.
So, is this diagram a single layer, or is this multiple layers for the transformer?
Oh, in this example, they have the multiple layers by this n times this.
Okay.
You can see that. So this is on the left is the encoder, where you repeat n layer times that particular architecture, and then the same for the decoder.
Okay. And then how do we get variable length output for this model?
Oh, so when you actually do the generation, not during training, but during inference, you do generate one word at a time. So you encode the source as you would do on the during training, and then you would have the attention over it to produce the first word. Then at the second step, you'd have the attention over the source plus the self-attention over the word that you generated before. For the fifth word, you would have the attention over the source, the self-attention over the previous four, and generate the next word. So the generation part is still done one word at a time.
Is it both the ends should they be same? Like if there are 8 layers over here, is it necessary that we have 8 layers over here?
What was the question?
Both the encoder and decoder, it shows n layers.
Yeah.
Should both the n be equal?
No. It's just in the original paper they got their best result with 8 thinking. Yeah, over a ton of data. Yeah.
So in multi-head attention in general, do we use all the attentions at once, or can we just sample from a few of them and weight them accordingly? Or what is the...
Well, so the way that this is implemented, right? Let's say you have, what they did is in order to keep the number of parameters down, they said, let's say we have 512 parameters that we want to keep. Then the weights, if we have 8, is it 8? If we have 8 heads, then we will use 64 for each of them. Yeah, okay, 64 for each of them. If we have 4, we will use 128 for each of them. So they reduced the number of parameters that each attention head has in order to have the same total parameter size, parameter number on the attention.
So in terms of capturing, say, long-term dependencies, which is better, one head with 512 or 8 with 64?
So that's an empirical question. I think that the answer is that you might need more heads because you won't only have long-term dependencies or only have short-term dependencies. So having multiple heads might allow you to learn both.
So is attention sort of linear in the number of words, or can you skip words and have like a bigraph, or you take attention over bigrams and trigrams rather than?
You could. That's not what they did, but there's some work where they attend over parts of the source that are either predefined or they're learned. So there's nothing, telling you that you have to attend over all of the source sentence or anything. Okay, so I think it's time for us to adjourn. There's a bunch of old quizzes here that you guys have to pick up, right?
Each file is a different day.
Oh,
Each file is a different day. Okay, so you can just select the day. So yeah, please don't mix. Yeah. Which number is it? 7? So yeah, that's the last one.
Yeah.
我的问题是，它一般怎么 solve？ 把光速变成0.9，其他均匀。对，差不多。就是相当于原来。它是有一个强度，然后又长的。
So, or they are trained by using the or like having them have different or even if they are they want
Yeah, I'm not like it.
or if you have in this case, they use the alpha function as a standard function to go into the copy model. So in the end, well, here they combine the predictions of the humans. Right? It was like having a.
Sorry, are these all? Yeah, so every parallel is supposed to be a different class.
Okay, because I can't find my. Oh, it's over there.
So I'm going to get few quizzes, but I can still check.
In a transformer?
Yes.
Okay.
So
just
I'm not sure how the decoder can know the order of outputs. So like there's no RNN, so there's no
Well,
hidden
okay,
state.
so there's a difference between training and inference. So which part are you unclear about?
So just for example, in training, so
Yes.
to generate the first token, basically I'm given the entire input.
Yes.
And somehow the decoder has to know it has to generate the first word.
Yes.
But it's not given like a start of sentence symbol or anything like that. So how does
Well, the start of sentence symbol, it's debatable whether you need it or not, either way.
Okay, yeah.
Because the difference here, why did we need the start of sentence symbol in an LSTM, right? Because the LSTM expects to receive two inputs, right? The context and the previous word.
Yeah.
So the only reason we used the start of sentence symbol was in order to have a previous word to provide to the LSTM when we started the generation.
Yeah, so it's just like a dummy.
Yeah, almost,
So for example, in later steps, so for example here, when I'm generating the third word, so somehow I have to know I've already generated the second word. So how is that done?
Well, the generation at inference time, it is done one by one. So we would encode the source, and then we will say, okay, now we are going to generate the first word.
Yeah.
Then we're going to generate the second word, right? So at every step, you know what you have generated before.
From self-attention?
Well,
I mean,
you would have.
From my understanding, there's not